So now let's put everything together. We've got our ALU operations, we've got our memory access, load and store, and we've got our instruction fetch. This is what our branch instructions use. And let's see what these operations do. So all of them are going to load the instruction. This is loading the instruction from the instruction memory. And all of them are going to calculate the next PC. So for all of these instructions, we're going to use the PC, we're going to use the instruction memory, and we're going to use the adder to calculate the next PC. Now all of these are also going to read the register file. So ALU operations read the register file to do their calculation, memory access reads the register file to find the address, and branch instructions read the register file to figure out if the two registers are equal or not equal. So all of these are going to read from the register file. But then they start doing different things. So the ALU operation is going to do its ALU operation, so add, subtract, and, or. The memory access is going to calculate the address, but it's going to do this using the ALU. And the instruction fetch is going to do a branch comparison. It's going to look at two registers, subtract them, and see if they're equal. So all three of these are going to use the ALU, but they're going to use them for slightly different things. Next, the ALU operation is going to write back to the register file with the results, and memory access is also going to write back to the register file if it was a load. So we're going to have some of these instructions writing back to the register file, but some of them don't. Now the memory access also needs to read or write the data. So before it can write the data back, it's going to have to access the actual data memory. The instruction fetch needs to do a few different things as well. It's not going to write back to the register file, it's going to update the program counter. So if you take a branch, we're not going to use the +4 value, we're going to use another value for the branch. And in order to get that value, it's going to have to calculate the branch address. So it's going to have some way to figure out what the branch address is, and there's a little bit of a problem here. We're already using the ALU to do the branch comparison. So if we look across these different types of instructions, what we see is that most instructions are using most of the processor, and they can reuse those parts. So we don't need to have separate memory access or register files or ALUs for everything. Most of these can reuse the same parts. But we also notice that instruction fetch we have a problem. We can't use the same ALU for both doing the branch comparison and calculating the branch address. So we're probably going to need another ALU for doing the branching. So now let's look at how we connect this all together. So here we have our register file and our ALU. We've already basically talked about that. You take the output from the register ports, you put it right into the ALU, and then when you take the output of the ALU and put it back into the register. You'll see in a minute why this line is so curvy. So now let's put in the memory. All right, so here's our memory, and now we want to hook that up. Well, what do we need? Well, we need some way to get data to the memory, and we know that comes from the register file. When you're doing a store, you store a register file value, and we need an address. And that address is going to come directly from the ALU. So here's our address from the ALU. And then finally, if we're going to do a read from the memory, we need to get the data out of the memory and into the register file. So we're going to need some way to get the data out and into the register file, and this is how we get the data from the memory to the register file. So now we've got this largely hooked up. Now how do we get immediates in here? Because remember, when we do address calculations, we're adding a register and an immediate value. So we need our sign extension logic in here, and the input to the sign extension comes from the instruction. So remember, that immediate field is in the instruction. We're going to sign extend it and then put it into the ALU. So this is how we get immediates into the ALU. Now here's a question. What is this 0 output used for on the ALU? Is this how we set R0? Is this how we sign extend the immediate? Or do we use this for deciding to take a jump? So this is the 0 we use when we're doing branch equal and branch not equal comparisons. So we do subtraction, and if the result is 0, then the two inputs are equal. Alright, so if you look at this diagram here, there are two places where red and blue lines sort of merge together. But we can't just merge signals, we need to choose one or the other by putting in a mux. So at these two locations here, we're going to have a mux that chooses which signal is used. So which signal goes into the ALU and which signal gets written into the register file. So let's put those in. Here's our first mux, and what does this choose? Well, this mux chooses the ALU input, whether it's coming from the register file or the sign extended immediate. So you can guess here that for R format instructions, we're always going to take the register file, and for I format instructions, we're always going to take the immediate value. We have another mux, and this is the mux here that's after the data memory. This mux selects what we write into the register file, if we write in data from the ALU or data from the memory. So you can guess here that for any load instruction, we're going to take data from the memory, and that otherwise we're going to take data from the ALU.